employees, and it is supported, financially supported by Wine Australia and the government of Australia. I would also like to mention that we have an plan of research of 8 years. I work on the field of generation of yeasts to improve the quality of wine. As you know, Saccharomyces cerevisiae is the main one used for the making of wine, for the transformation of the must sugars into ethanol and CO2. But at the same time, this yeast creates or produces secondary metabolites such as acid, higher alcohols esters, and CSV. Even though these are in a very small amount, they are very important for the flavor of wine. I would like to highlight that for over 60 years we have developed and isolated strains of yeast in order to provide options for enologists to differentiate their wines and to have non-risk fermentations. So where do these yeasts come from? The most common and traditional method is to isolate dominant strains of the difference in color is thought to be attributable to a natural mutation that happened many centuries ago in the Pinot Noir variety. As in this example, this mutation happened naturally or spontaneously in nature, but at a very low frequency, and that is why we use mutagens in laboratory to accelerate this frequency. You can see here a physical agent of this. An example of physical agent is UV. The dose is critical. We would be applying the common expression, what does not kill you makes you stronger. If we used a higher dose, most of the population would die, and then the survival would show multiple mutations, increasing the chance that the relevant aspect that we need in the enology would be negatively impacted. However, too low a dose would not be enough. That is why it is so important to identify the needed optimal dosage. In general, to create diversity through mutagenesis is a relatively simple process. Later on, we find in our hands a lot of multiple molecules, but we need to apply selection. For that, we need that the strains with the desired feature have a particularly selective advantage. When we apply the selective pressure, only cellules with the desired phenotype will be bad smell of rotten eggs. We know that they are responsible for the production of wine yeasts are responsible for this compound. Some years ago, during a research between AB BIOTEK and AWRI, we were able to develop yeasts with low H2S. How? Well, we subjected a process. The darker the colony, the bigger the production of this compound. After a cribbage of more than 16,000 colonies, we were able to identify 8 strains with a more clear phenotype than the other strain, as you can see in the image. This phenotype that has hydrogen sulfide in a low content was cultivated in a Riesling variety. As you can see here, the PDM strains created detectable levels of H2S during alcoholic fermentations, whereas in one of the isolated strains created much less of this compound as compared to the PDM control strain. So a few years ago, this strain was commercialized commercialized by AB AWRI, and it is recommended for the elaboration of fruity wines, even in musts with a low concentration of nitrogen. And the removal of reductive notes enhances the varietal nuances of the wine. Now, talking about the second example with the overproduction of floral aromas, this is a desirable attribute because it is a trend among consumers that they want fruity and floral wines. One of the compounds that is produced during AF is 2-phenylethanol, or 2-PA, that is linked to the rose or floral aromas, and it is derived mainly from the catabolism of amino acid phenylalanine. And it can be esterified by the yeast to produce the 2-acetate phenylallyl. What is the contribution of these compounds to the floral compounds? Here you can see the difference of the two compounds in two different varieties of wine, red and white. This shows a certain impact of these compounds to the aroma of the wine. The value of the activity of phenylacetyl, of the so not treated strains were also implemented with the hope of having spontaneous mutagenesis. After several days, we were able to isolate around 73 resistant strains. These strains were used to ferment a very small volume of a synthetic must, and around 20 of these strains showed very intense aroma at the end of fermentation. These strains were then used to ferment a small amount of a Chardonnay must, and the levels of floral compounds 2-PE, their aromatic characters, or more intense aromatic characters, and also wines fermented with Rosa 1 created a very intense aroma. On the other hand, the notes of red berries and red fruits were masked, and this resulted in wines that were considered less balanced than was expected on a red wine. This graph summarizes the production of 2-PE by Rosa 1 and Rosa 2 in the different vinifications over 5 harvests. And you will see how in all the varieties of studied wines,
in order to prove whether these mutations give out as a result a change in the ethanol content, we've used the CRISPR-Cas9 genetic sequencing technique, which allows us to introduce these changes in an individualized way in a strain called AWRI 1631. Once these strains were used